or to give you an introduction into integrated water resource management, in particular today into industrial wastewater. And this part of what we will discuss or present today is embedded into a larger project, which is funded by our Ministry of Research, Education and Research, and in cooperation with Isfahan University and the University of Technology, and University of Isfahan. So it's part 3, as Jonas just mentioned. We counted the presentations which have been given in Berlin by the 2 colleagues recently, and therefore it's part 3, but it's not so important. Maybe some words with respect to me personally. My name is Sven. You can simply call me Sven. I know it's very difficult to pronounce Geißen, but Sven is more than sufficient. I am educated mechanical and chemical engineer. I worked in industry for a certain while, returned back to university, finished my PhD, and was appointed to become a professor at TU Berlin in the year 2004. Since then, I'm working in the field of particular industrial wastewater treatment and recycling, but also partly in the field of municipal wastewater treatment, for example, in the field of elimination of micropollutants and energy efficiency, anaerobic sludge digestion, excess sludge reduction, excess sludge production, reduction of excess sludge production, etc. Besides this, I'm a member of the board of German Water Partnership, which is an association with about 300 members, particularly small and medium-sized enterprises, which might also, let's say, assist you in solving water-related challenges. And I'm also at the moment vice chair of a specialist group of the DECHEMA. It's an association located in Frankfurt, an association of the process industry, where members like Bayer, like Covestro, like BASF are included in this specialist group, where we are defining, for example, possibilities and opportunities to move into zero liquid discharge or minimize liquid discharge, or giving an outlook into industry 2033, looking a little bit into the future, etc., etc. So, and I know, please, Jonas, switch on your phone. You can introduce you personally and followed by Azad. So start, Jonas, to introduce yourself briefly.
Yeah. Hello, my name is Jonas Pluschke. You can call me Jonas, is the simple version for the Iranians. I've been working with Professor Geißen for over 3 years on industrial wastewater treatment systems. I will present 3 containerized systems for development or innovative treatment systems that we have been working on for some time, in the last 3 years. I think for now that's
okay. Thank you, Jonas. And Azad?
Hello everyone, my name is Azad Resman, or in Persian Azad. It's very nice to meet you all. I am a research assistant and studying my master's in environmental engineering, and have the pleasure to enjoy a lot of classes of Professor Geißen in wastewater treatment. So that is my specialization, with also circular economy. I'm very happy to be here, looking forward for this presentation.
Okay, thank you very much. A short introduction into the activities of the chair. So very briefly, I guess you all know these processes. We are working on membrane processes for wastewater recycling, different type of membranes, also in combination with electric fields like electrodialysis or electrodialysis metathesis, but also in the field of conventional membrane separation like microfiltration, ultrafiltration, in particular nanofiltration to reverse osmosis. We have a long tradition in the field of AOPs, advanced oxidation processes, or you can name it oxidation processes in general, where we also developed systems for the dissolving of ozone, efficient dissolvement of ozone into water, and catalysts. We are working on catalysts for ozonation and applying H2O2 in combination with iron, the so-called phantom process, etc. So we'll hear more details about selective recovery of valuables from wastewater, which is also a field where we are active since more than 10 years, trying to collect or to separate selectively substances which have a certain value out of effluents. This solves basically two challenges. One is the pollution of the wastewater is reduced, and secondly, the financement, because wastewater at the end of the day costs money, and no one is really willing to pay for it, except you have legal requirements or except you have a shortage in water supply. Biological processes, from my point of view, are the major processes all around the world, or because they are, let's say, mimicking the natural processes. They are highly efficient, more efficient than the man-made processes like membrane filtration or oxidation. So they are natural processes. They're working on anaerobic and aerobic processes. And in this context, we have developed new bioreactors, as shown here, for example. This is a plant located in South Korea, treating effluent from a chemical factory. Nowadays, there are more than 60 full-scale plants with volumes of about more than thousands of cubic meters installed. And last but not least, we are modeling at different levels. I will give you a short introduction later on. Modeling and simulation is and will be very, very important because the systems are becoming more and more complex, in particular when you're talking about wastewater recycling but also simple municipal wastewater treatment plant. It's worth to model. And what we are doing inside this project, inside this IWRM project, the Integrated Water Resource Management project, we are modeling the whole region around Isfahan. So the catchment of the river Zayandeh Rud, and we are able to predict in the whole group, which is not introduced today, the development of the water supply in the future. So, and this is the overall project goal: development of a sustainable water management concept for the Zayandeh Rud catchment area, combining the competing interests of all stakeholders. The partners are mentioned here. The coordinator is Inter3, Institute for Resource Management, located also in Berlin, like we are located. But as you might know, also DWA, that's the German Association for Water, Wastewater and Waste, and Hamburg Wasser, and I think the other institutions you know, you can identify them here. For example, the Isfahan Regional Water Company. So I'm heading now over to Jonas.
Thank you. As Sven just described, the project IWRM, one of the results is a visualization of the catchment area, so the area around the Zayandeh Rud. And here you can see in green the vegetation across the Zayandeh Rud. It's about 36,000 hectares of vegetation. Am I clicking, bitte? And the development, you can see.
Oh, sorry. Yeah, no, again.
So here you can see the development of the green area, especially in the agricultural area, over the last, I think, 12 years. And this reduction is a problem because it's food production, and moreover, the industrial stakeholders in the area. You have a lot of strong industry in Isfahan, refinery, steel production, power plants. They need new alternative water resources. You have a mega project in providing desalinated water from the Persian Gulf. This is one option to find alternative water resources. But imagine the prices of water that is pumped for over 1,500 kilometers. It has to take 1,700 meters of elevation. So you need to invest a lot of energy to produce these alternative water resources. Another option, and that's what we are focused on, is recycling industrial wastewater and trying to reduce the water footprint of industries. Okay. So this is just the overview of the role of TU Berlin in this project. So we have production integrated modeling. This was done with mainly with our partner Isfahan Steel Company, which was initiated by APFA, the Iranian organization for the wastewater collection and sewer management. Then we have support for construction and commissioning of large-scale plants. This is goes in the direction of consultancy. And then we have training modules. And this event here is part of the training module, Industrial Wastewater as a Resource. We have had a very good training module on membrane processes about 2 years ago, and the reuse of municipal wastewater for the industry. This is actually a topic where the Iranian, where Iran is very strong. And I have seen in the last week numerous high quality water reclamation units which use treated municipal wastewater as a resource. Yeah, so we are industrial wastewater. So this is the timetable for today. We are about on time. The introduction is this presentation. I will continue with presenting 3 innovative industrial wastewater treatment systems that we have dimensioned, built, planned in the last 3 years. And so it's the project InnoVa in Tunisia, this project SUSPIRE in Tunisia, and the project HighRec in Qatar and Iran. So I think I will quickly, afterwards we have the presentation by Professor Geißen. He will present some key topics of industrial wastewater and especially wastewater reuse, looking at different perspectives. And my colleague Norman Schweimans, he's an expert for automation, digitalization. He will talk about a digital twin for industrial wastewater treatment plant, which is a possibility to not only react, but to predict operation parameters. So this is something that is very interesting, for example, for energetic optimization, or also for the reduction of chemical usage. And we will finish up by an open discussion, ask the experts. We have the opportunity to share ideas and discuss points. Okay, thank you. I will now begin my presentation on the containerized industrial systems. You can see the presentation?
Yes.
Yes.
Okay. Good. So IWRM, that's the project, as you all know. Currently, I'm at the University of Isfahan in Isfahan, and we have we have been cooperating with the Isfahan University of Technology, and I'm thankful that it's possible, due to our fruitful academic cooperation, for me to be here. Okay, so the 3 projects I will present are listed here. The first one is InnoVa. It's a project in Tunisia. It started in 2020, and the main goal is valorizing olive mill wastewater. So we try to selectively extract high-value biomolecules produce biogas and recover nutrients. It's a very circular economy approach and a biorefinery type of process. The next project I will present is SUSPIRE. It's also a project in Tunisia. I spent the whole of June this year in Beja, in the north of Tunisia, to install this system. The project lead is Maximilian Philipp, a colleague of mine. And the project idea is water recycling from slaughterhouse wastewater. So we take industrial wastewater from a poultry slaughterhouse and try to produce high quality process water using a number of processes. And the third project, which is very interesting probably for Iran, is HighRec. It's a project where we aim to recover clean irrigation water from brackish groundwater with reduced chemical usage and usage of renewable energy. So a big focus on sustainability of the process. So InnoVa. InnoVa started in 2020 due to Corona and other factors, shortages of supplies. It took 1.5 years to finalize the pilot plant. In February 2022, last year, we managed to import it to Tunisia. And in the last season, so we began production in October, we treated about 12 tons of olive mill wastewater. The project is a project between TU Berlin, represented by Professor Geißen, and a long-term partner, Professor Sami Sayadi from the Center of Biotechnology in Sfax. The process was awarded the German African Innovation Incentive Award. It's an award for very innovative research from Africa, sponsored by the Federal Ministry of Education and Research, Germany. And the project is managed by the DLR. We worked together with a company, Delta Umwelttechnik. They constructed most of the system, and we had support by Endres & Hauser, which is a known company, I guess, in Iran as well. Artec Innovations, a ceramic membrane producer, and many other companies. So what is olive mill wastewater? We have to briefly look at what is olive oil production. We begin with olives. After storage and washing, you need to remove leaves and then crush the olives. The crushed olives are malaxed, so mixed at a certain temperature for some time. And then at some point, a decanter or centrifuge will remove the oil from the solids and water. So at some point in the process, we will find wastewater. And this is the wastewater we try to treat. Okay, what is olive mill wastewater specifically? It's the fruit water of the juice. So the olive is a pretty dry fruit. It grows in very dry, arid areas. And to cope with the stress from dryness and the stress from UV light, it produces a lot of oxidants, antioxidants. And these can be found in the fruit water. What are the current solutions for fruit water or olive mill wastewater management? The main or a classical one is disposing it untreated into water bodies or the Mediterranean Sea. A method which is still applicable for small-scale farmers is using it as irrigation water in olive groves. This is possible as long as you don't have intensive agriculture. If you have reach a certain intensity of the olives, the soil will be damaged. You have salts, you have fats, you have the accumulation of biomolecules, and in many areas in Spain, for example, or in Palestine, I know examples where the soil is degraded so much that it cannot take up any water anymore. And then a method also very well known in Iran is the evaporation pond. often used for reject water from RO systems. This water in Tunisia is often also discharged in large evaporation ponds, and the arid climate reduces the volume to more or less a solid. So this is a flow scheme I prepared in my master thesis. It looks a little bit rough, but this was the first plan on, okay, how can we valorize this wastewater? Simplified, we have a storage of the raw olive mill wastewater. If needed, enzymatic treatment is possible to degrade large polyphenols into smaller monomers of higher value. Then we have a mechanical treatment and ultrafiltration. We upgraded the system so that these components are now also used for the anaerobic digestion. The permeate of the ultrafiltration, so about 75% of or 70% of the initial amount is given into an adsorption column, and the bulk will afterwards go into a storage and be the feed for anaerobic digester for biogas production. In many other countries, the gas prices are much higher than in Iran, and so the production of biogas is often an economically viable option. The reclamation of the polyphenols is then done on the adsorption column. We use an organic solvent to desorb our target molecules and further purify and concentrate them. So we built the system together with Delta Umwelttechnik. So it's a containerized olive mill wastewater treatment system with selective biomolecule extraction and biogas production. So we have a mechanical pretreatment, we have an ultrafiltration system, we have the adsorption column and desorption column. This whole system is explosion safe because we work with organic solvents. We have a solvent recovery system, and provided by our Tunisian partner, we have an anaerobic digester. This is a very short impression of the system in Germany before shipment. As you can see, it was a bit cold. Yeah, so these are some impressions of the system before the export to Tunisia. In June last year, we had an opening ceremony with many stakeholders from different areas of Tunisia and different backgrounds. And we finally could begin operation. So the olive mill season begins in October. In November, we started with a team of 3 master students from Germany and the team from Tunisia to start learning on the real life application of the process, and started optimizing as well. And the goal was achieved. We managed to recover polyphenols of high value, and we're currently still trying to further purify them with different assays and trying to find commercialization. Finding a partner to utilize them on an industrial scale. Masoud and Hamid, do you want to translate at this point? Because
thank you so much for your nice presentation. Yes, of course I can do it. خب خیلی ممنون از حضور همگی شما توی این جلسه. همونطور که دیدید توی این چند اسلاید پروژه‌ای که توی تونس در ارتباط با استحصال مواد با ارزش از پساب در حقیقت صنعتی که زیتون رو به در حقیقت روغن زیتون تبدیل میکنه انجام دادن و جزئیاتش رو خدمتون گفتن و در حقیقت نکاتی که راجبش بود از جمله اینکه پلیفنول ها رو با یک پروسه‌ای از پری تریتمنت ها گرفته تا استخراج با حلال های عالی که توی فرایندشون استفاده کردن تونستند بازیابی بکنن و فلو دیاگرامش رو هم خدمتون نشون دادن. در انتها اگر که سوالی راجع به این قضیه یا این پروسه داشتید توی اون بازه زمانی که برای پرسش و پاسخ در نظر گرفته شده میتونید سوالاتتون رو بفرمایید. Yes, Jonas, I guess it's enough for now.
I see. Okay, so the next project I will present is SUSPIRE. This is a project that is currently running, and the system is being optimized at the moment in Beja, Tunisia, in the north of Tunisia. So there were three main components to the installation, which I was in charge of in June this year. The first point was upgrading the existing biological treatment system. So you can see the image here. This was a biological treatment system constructed for the poultry slaughterhouse. We had new aeration panels. We will have a new compressor, and we have a new measurement equipment. Then we have the installation of a water reclamation unit with an ultrafiltration system for biomass separation, and a reverse osmosis system for process water production. So we can say it's an MBR system with a side stream, I think in English you call it side stream filtration of the biomass. So the membranes are not submerged, but in normal modules and are just fed from the tank. And then the third point is the installation of solar panels. This is something that I recommended already to a lot of my Iranian partners and that I had a chance to talk to. Solar panels are able to produce very cheap electricity, and we try to improve the sustainability of our systems, for example, by incorporating solar panels. And we installed about 50 kilowatt peak together with our industrial partner. So this is Maximilian Philipp. He had his first child this year and was on paternity leave, and I took over in the crucial phase of installing the system. The idea is using process water for the slaughterhouse. This generates wastewater. Then we have a mixture of a flotation and MBR system to treat the organic components and remove most of the or some of the nutrients. So we are left with a water that mainly contains ions, and we use a reverse osmosis system to produce high quality process water, which can then be used in the process again. Meanwhile, we try to use biogas and photovoltaic to generate energy for the process and use the residues for agricultural purposes. The project is funded by a line that's called Tunga 2+2, and the reason for that is we need two Tunisian partners, so one research partner, which is the Centre de Recherche et de Technologie des Eaux, which is a research center about water, and we have an industrial partner, which is the slaughterhouse. And then we have two German partners, and this is the TU Berlin, represented by us, and Delta Umwelttechnik, again the site constructor. And the whole project was financed by the Federal Ministry of Education and Research Germany, from the German side, as well as some funding by the Tunisian side. And the DLR is the project coordinator. So this is kind of the flow scheme. We have a typical slaughterhouse wastewater with about 4 to 5 grams of COD, about 60 cubic meters per day. So it's small scale. This is one of the ideas. It's decentralized. And one of the advantages of decentralized systems is the water system in general becomes more resilient. The direct opposite of it is, for example, bringing desalinated water from the Persian Gulf. This is a very centralized system, and if you have issues with the desalination system or the pipeline, a lot of issues can be created. With decentralized systems, the general system can be a little bit more able to react to change. That's why we are interested in researching and trying to provide case studies for these decentralized systems, even if they might be less economic to a certain degree. Then we have the wastewater is given into a mechanical pretreatment, drum screen. We have a homogenization tank. Then we have a dissolved air flotation, a process which I am a big fan of, because you can, depending on the wastewater, remove a large amount of the organic matter with very low usage of chemicals, if at all. You don't even, some DUFs work perfectly fine without any chemical addition. And then we have an aeration system. We have a ultrafiltration for recovering the biomass. The permeate of the ultrafiltration is given into a reverse osmosis system, and we produce about 20 cubic meters of permeate per day, with roughly 50, or the goal is 50 microsiemens per centimeter. So this is images from June. One of the important works was, for example, installing the new aeration panels. So these are high-tech aeration panels from Germany, which use membranes to diffuse very, very small bubbles and have maximum efficiency in the oxygen transfer from the air to the liquid. So we were able to produce a very, much more efficient system by increasing the oxygen transfer. So this is the container. It arrived in end of May, I think. We had trouble with the douane, as always. It's not easy to import and export such sophisticated systems. And by now, the whole system is functioning at 100%, and we're slowly starting up the reverse osmosis system. So because university, we always have a component of teaching. So in the beginning, it always looks a little bit rough, but we always try to bring students with us to give them the opportunity to have a real-life application experience. And my experience is that students profit a lot from participating in such projects. On the right, you can see me after the first time we produced high quality permeate. I was Tunisia also experiencing a heat wave at the moment. So we had around 45 degrees. You could not work during the daytime. We started early in the morning and had about 6 hours of break during the daytime, and started working again at 6 in the evening until late at night. And we are able to treat 60 cubic meters of poultry wastewater to a discharge quality, much better than the quality it was before. We have a fully automated production of 40 cubic meters MBR permeate, is quality-wise definitely good for irrigation, still containing some nutrients. And then about 20 cubic meters of high-quality processed water per day is what's possible at the moment. We try to increase this value, but for now, we are happy with the system as it is. Okay, do you want to translate again? This is the last slide for SUSPIRE.
Thank you, Jonas, for your very nice presentation. As I remember, we had the discussion last night about the translation, and I see the audience mostly postgraduated, and last time there was a correspondence from a news agency, and I was forced to translate, but I think if the audience have any ambiguity or any unclear, they want to clarify more, they can ask the question. I suggest we continue because the slides and your speech are all clear.
Wonderful.
Thank you.
Thank you. Okay, then I continue. So this was the SUSPIRE project. For me, I enjoy these very practical part of the job, but it's not always very easy to bring such technologies to foreign countries. And I'm very happy that we have a third project where we will try to bring such a system to Iran. And this system is part of the HighRec project. HighRec stands for Intensification of the Recovery Ratio in Brackish Water Desalination Systems for Agricultural Irrigation. So we want to produce water for irrigation from brackish groundwater. We have a very strong team. So the funding comes from the Middle East Regional Water Research Cooperation Program, a program by our Federal Ministry of Education and Research, Germany, which aims to highlight the Middle Eastern region, especially regarding water research. And FONA is a research for sustainability. So we have a very large focus on general sustainability of the processes. And Fraunhofer is a very prestigious German research center, in this case specialized on solar applications, solar panel applications, and so on. So here you can see the project partners. Fraunhofer, as I just said, they're in the south of Germany. The south of Germany has a lot more sun than the north, but still has a lot less than Iran. And still we managed to produce very cheap solar electricity. And a lot of the research is on solar panels is done at the Fraunhofer Institute. Joachim Koschikowski is our partner there. Then TU Berlin is among the partners. Of course, Inter3. Inter3 is also the managing coordinating partner of IWRM. And for all projects in Iran, it's always good to have Inter3 in your team, represented by Shahruz Mohajeri, a institute that has been working in Iran for over 15 years, I think. Then we have the Qatar University, represented by Dr. Sami Sayani. This name also already popped up. This kind of shows the importance of networks. He was also working in Tunisia before at the Center of Biotechnology. Then we have the University of Biljand as partner, represented by Dr. Mohsen Poureza, and Isfahan University of Technology by Banafsheh Khalil. So this is the team, and the idea of the process is, first I want to introduce Lina Streckwall. Lina Streckwall is a colleague of mine. She's the main responsible person for it. I have just certain roles in the project. So I quickly want to go through the plan. We use brackish water, some brackish water supply. Theoretically, this can also be treated industrial wastewater, but we are looking at brackish groundwater. One focus point is the pre-treatment. Pre-treatment solutions can often be much more cost efficient than end-of-pipe solutions. So we look at innovative pre-treatment options. Then we are looking at a closed, we are constructing a closed loop reverse osmosis system, which is a reverse osmosis system generally, but with a recirculation of the concentrate up to a certain threshold salinity. I will explain a little bit more about it later. Then we are looking at the brines. So we need a post-treatment. Maybe zero liquid discharge is something a lot of people talk about. I think minimum liquid discharge is more what we are going for. And the freshwater we are, of course, always in discussion with our experts from the agricultural sector to get irrigation water, which is capable of sustaining the fruits. To increase the sustainability of the whole system and the stability of the process and the general output of the process performance, we use intelligent control. So PLC, I think is what you say in Iran, programming language control. And we again try to use PV as a supply, especially to also have a system which is capable to not use any electricity from the grid. So there's two regions where we're going to test our system. One is in Al Khor in Qatar, which uses hydroponic systems for the production of vegetables, and already has a desalination system running. So we can compare the performance of their system and our system. And then the other region in eastern Iran is Birjand for the production of saffron. So these are just the key points of the HighRec project. We want high flexible solar-driven desalination system. So the flexibility of the system is important. We want dynamic adaptation to changing raw water compositions. This is something we learned, or was new to me, that the water composition in the groundwater can change over a year in certain cycles. And then we have the concentration of the concentrates to the maximum possible to a threshold salinity, and therefore maximize water recovery. And the focus points are the chemical reduced pretreatment technologies. So we are looking at electrodialysis metathesis and capacitive deionization, ion exchange systems, or nanofiltration. We had a very successful project where removing of hardness using nanofiltration was a good option. Then technical and economical evaluation of minimal and zero liquid discharge concepts. And of course, we always try to have a holistic technology transfer program where with operational and maintenance courses to have a sustainably running system. Just one example of an innovative pretreatment, we are looking at electrodialysis metathesis. It's a process that uses alternating anionic and cationic membranes and a DC current to separate these charged particles or ions. And it's a process that doesn't use any pressure, which reduces the fouling a little bit, and which is used mostly for high valuable ions. But with increasing technology ready level for the system, we're starting to see application for reject water from reverse osmosis systems. So the value was given between 2 and 15 kilowatt hours per cubic meter treated water. And we end up with a chloric concentrate, which contains all of the hardness, so calcium, magnesium, and sodium. And then we have a sodium concentrate, which contains the sulfates and carbonates. So we managed to separate the covalent anions and covalent cations before going into the membrane, and many times calcium, magnesium, as well as sulfate are the ions that will produce scaling. In some cases, silica or other ions can be an issue, but this is a good pretreatment to remove hardness or to separate the ions. So we started constructing our closed loop reverse osmosis system with the company Boreal Light. The idea is you have a normal membrane system, you concentrate the feed and you circulate the feed. The whole time permeate is produced, and then when you arrive, so the salinity in the feed increases step by step, and instead of doing 2 stages or 1 stage, you go increase the pressure step by step, and you can go much higher than with a single or two-stage RO system. So the brines can go up to 100 gram TDS per liter. This is the plan for the HighRec system. So we want to produce, we want to bring about 50 kilowatts of solar panels, and the whole rest of the system will fit into a 20-foot container. Sabas, I think? No, I want to thank you, and I am open for questions if there are any. Merci.
Thank you, Jonas, for your nice presentation. I think you can ask question, and I have some question for the MBR system, as you said, in slaughterhouse, as well as in the Tunisia. It was interesting, both the olive mill and slaughterhouse. And I have a question on MBR system, which was, as you said, it's an external system, and many books or references suggest or preferably suggest the submerged system. I want to know why did you choose this system at the design stage, and how did you manage the fouling problem, because it's not submerged and it's outer? Yeah. Yes.
Okay. Thank you for the question. So one point is, or one of the advantages of having a separate membrane system is you can go at a higher velocity. You can pump the water at higher velocities, which improves your the management of the covering layer on the membrane. Inside of in submerged systems, you have the air bubbles to create turbulences, but the speed is not very high, the velocity of the water. So this can be one advantage when regulating the system. The cleaning in place is much easier because you don't have to take out all of the membranes and put them into a separate smaller tank. But you can just empty the system, fill it with water, and use the installed SIP system to more or less regularly chemically treat the membranes. So these are just 2 points which have an advantage. And in our case, it was also because we are at a rural area of Tunisia. It's decentralized system, and we will bring high-end technology. And installation of submerged membranes is not very simple. If we do it separately and we already finish installation inside the container, the whole system is ready to go once the container arrives, more or less. So this was a few of the reasons why, in our case, it made sense.
How much was the MLSS of your
system? Yeah. So
aeration time.
We began at a very low rate, of course, and our calculations was based on 10 grams.
10 grams.
Wow. 10 grams. That's what we based this whole system on. Do you want to add something?
Yes, I think that's a general question. You're completely right. Now, whether to choose a submerged system or a cross-flow system. From the experience, I think both systems we started in the 90s with the cross-flow systems in the treatment of landfill leachate wastewater effluents, and then we moved into industrial applications, and then finally also in municipal applications. But basically, the submerged systems has the great advantage that they are much cheaper and that they have less energy consumption. No? But you need more surface area for sure. No? So the specific flux or the flux through the membranes is, let's say, for submerged systems in the range of 15 liters per square meter an hour. And then for the cross-flow systems, about 80, 90, and in the best case, above 100 liter per square meter an hour. But they are consuming more energy. But they are much more resistant, as Jonas just said, against the layers. So the layers can be better controlled. So if you have, let's say, any concerns about the deposition of substance on top of the membranes, you should use a cross-flow membrane filtration system. So for me personally, I would say to keep it simple, municipal wastewater, every time, if you would like to install an MBR, a submerged system, or for industry, usually apply a cross-flow system. No, because it's much more better to maintain. The maintenance is easier, as Jonas just mentioned, and the cost. Finally, the higher energy cost is not so. Let's say not so much important in the industry because we're talking about smaller flow rates. And the rejection, by the way, another point is, which I didn't mention so far, and Jonas also not mentioned, I completely forgot, is the higher rejection. So we have now just finished a PhD thesis in my team, where the lady compared for one industrial effluent, MBR, submerged, and a cross-flow MBR, with respect also to control the surface layer to have a higher rejection. So usually the rejection for the cross-flow system is higher because you have more condensed surface layer on top of the membrane. The deposit layer is more compressed, and which is additionally acting as a rejection. Yeah? And we do not know at the moment, that's a scientific question, about the biological activities in this deposit layer. There's also an assumption or hypothesis that inside the deposit layer, there's also biological activity in a biofilm, let's say called biofilm. But the rejection finally permeate quality is better for a cross-flow system. That's for sure.
Yeah, the addition of the covering layer as a filtration media is a interesting topic, especially when talking about biomass. Thank you for the question.
We visited, as Professor Geißen may know, that we visited one of the industrial plant in Isfahan was operating submerged system, and Jonas suggested to convert it to UF system, and it was our question how to change it, and I had some suggestion to change the system of submerged to external.
Maybe I can explain really quickly because it's a very interesting case. They are currently using 2 grams MLSS in their MBR system because they have a aeration tank and a whole biological treatment in front of the MBR system. So they go in with a very, very low concentration. And my thought was, okay, just separate the biomass with a sedimentation before the MBR system and use the MBR as an ultrafiltration without biological system.
Okay, thank you.
I'm not sure.
This has a disadvantage that you're separating the good settling. That means the flocks with a large size you're separating, and the single bacteria you're leaving for the MBR. And this might cause at the MBR a very, very condensed deposit layer. Because the particle size is smaller. You make a particle size separation in sedimentation. But this is a very, very special question now. And I think maybe for the audience, it's not so interesting going too much into the details.
Yeah. And there was one question from the chat, I was told, regarding the sanctions. Yes, the sanctions are, of course, a big issue, especially for membrane water reclamation. I was at 5 different water reclamation or 4 different water reclamation units, and all except one had trouble getting, especially the American-made DuPont or Dow membranes. In our case, the system is still in Germany. The pilot will go to Qatar end of this year, and we will see if the sanctions allow the importation to Iran or not. We still have to find out. I think I will.
Should be no problem. So the information so far is that it should be no problem because it's not dual use, and secondly, it's research. That's the information we received so far. But it's let's wait. No? So we do not have a final decision on this issue.
Perfect. Thank you, and I think Sven, you can continue.
Maybe we have some more questions because we are still good in time.
Yes, there's a question or
Yeah.
a raised hand. You can use the microphone if you want, or write it in the chat. Or raised hand by accident, I'm not sure. I think she's connecting. Okay, I'm not sure.
Hi.
Hi, we can hear you.
Thank you for your clear and useful presentation and your information about polyphenols. It was very noticeable because I study about polyphenols as inhibitors from lignocellulose that we are using as a substrate from fermentation. And during your presentation, I skimmed your review article about the polyphenols. But I have a question about the recovery of the polyphenols. In your deep information about this, they just using MF and UF systems, and I would be very appreciate that. Give me more information about this.
Mm-hmm. Yeah, this is a process that I've been working on for a long time, which there is no publication about it. This was one of we are not sharing too many informations at the moment because the process is still developing. But the core is a membrane filtration and a selective adsorption-desorption. So this is the key component, and then we try to play with a lot of operational parameters to improve the purity and then get to a point where it's actually valuable. And another point is to reduce the inhibition of the anaerobic digester. So at certain concentrations, the polyphenols inhibit degradation. And so the goal is not only to retrieve the valuables in a high quality, but also to reduce the inhibition so that we have a very high reaction kinetic in our anaerobic digester.
Thank you.
Thank you. Okay.
So any more questions? Last chance? No, not the last chance. You have an additional chance to ask questions at the end. That means at 3 o'clock.
I can ask a general question for especially desalination project, which is the main concern about the desalination project is the sustainability, which they are very highly energy consumption, energy intensive, and especially when with the target of ZLD, it is. I think it's cannot consider it would be a sustainable solution for our future. What do you think about that?
You mean the big project, the mega project of Iran, or do you mean HighRec?
Generally, when we are discussing about desalination, for example, in your HighRec, you had about more than 10 kilowatt hour per cubic meter.
Yeah.
And
so
the energy consumption is high.
Yeah, the question is very relevant and very, very good question. I think you cannot think these processes without also thinking renewable energy. This is one of the key points. That's why we always try to incorporate, or we aim to incorporate renewable energies, because the sustainability of the process is reduced a lot without renewable energies. And when it comes to zero liquid discharge or or something like this. When you look at the mass balance of the salts of a country, for example, at some point you need to deposit salts. And the question is, are these salts going to be usable in a high quality? Or is it okay to have a mixture of salts with a certain water content, and we have good landfilling systems, or old, for example, in many places you can find old mines for salt, and you can just fill them back up with salts. So the question is, the mass balance, at some point salts have to be taken out of the system. Otherwise it's not possible.
Okay.
This is what I would say.
Yes, of course. Yeah. Thank you.
Okay, then now we are in time, 1 minute beyond, so it's quite good. Thank you, Jonas, for keeping in time, and thank you all for this discussion. And I'm moving now to my my presentation, but I need the right to do so. Again, I don't have it at the moment.
On the right, there's next to the hand, there's
yeah. Now I can do it. Thank you. Gave me the allowance to do so. Okay, so let's just start the presentation. Oh, it's so you should see now my presentation on industrial wastewater treatment and recycling. Thank you for the feedback. Yes. Yeah, well, on the picture, I think you two colleagues from Isfahan, you know the campus of TU Berlin. You can see the TV tower here in the back, and the main building of Technical University here in front. And this is campus, and we are located, Jonas and me and Norman and the other guys who are attending this conference are located here, where the chimneys, you can see the chimneys here. That's the old power station of this area. And there we are located in this very nice building. So, yeah, this is something with respect to Berlin. So would be very nice to have you in Berlin, to invite you to Berlin, but I know it's quite difficult. And hopefully in the future it will be easier. Berlin is, I would say, the largest village all around the world. You can see here a lot of green. It's a park, one of the many parks we have in Berlin. We have a lot of waterways inside Berlin. So I would say you don't see any skyscrapers like in New York or in Seoul or wherever. So it's more a village than a million city. However, moving into my presentation, I will start with introduction. I will give you an overview on brackets wastewater or water, because water is contained in wastewater, and that's something which we have to address. And last but not least, the interaction of industry between industry and municipal wastewater treatment plants is also quite interesting to discuss this a little bit. So introduction. So again, what we are doing, I already mentioned, but I would like to give you an insight in what we are exactly doing, or not exactly what we are doing in many, many applications. So we are starting with these kind of plants. It's acrylic glass. So you can see inside is a bioreactor not filled with biomass at this moment where the picture has been taken. But it's very important for us to have a insight into the system, to use our senses, to use our eyes, to use our nose, to use our ears, to use our taste in some cases, even in most cases not for the wastewater, but sometimes you should use also your taste. So that's something which is very important, to use your taste. We have highly sophisticated measurement devices, but our senses, the human senses, are unbelievably good, unbelievably good. So, but this is not the story I like to tell you. I just like to address again that we are moving into the scale up. So integration into practice, that means challenging. We are talking here about a water column height of about 1 meter. And in this reactor type of reactor, we are talking full scale about a water height of 12 meters approximately. And that's what we are doing. We're transferring technologies from the lab scale, bench scale into practice. No? So you have seen some examples, and hopefully in the future, the examples Jonas gave will also be installed at full scale without external funding, just with private money. So, what is the water situation in Germany? We have summer now, and just today there came some news with respect to our groundwater level. Even in Germany, we are many concerns about the groundwater and the water supply, in particular in the region around Berlin. And this is the spokesman of the Green gave a short sentence. It was last year, when we have such times of water scarcity, priority must be given to public water supply quite consistently. And this is a question also addressing to Isfahan or to Iran or to the whole region in general. Who gets the water finally? If there's water shortage, what is the priority of water supply? And this is a real challenging question finally. And this is something which has to be addressed very early to answer this question. And we have another comment from the vice chairman of our party, CDU-CSU parliamentary group in the German Bundestag, Stefan Bilger. If power plants need to be cooled, then that is in all our interest. If agriculture needs water to grow food regionally, then it's also in all our interest. And that's something which you can transfer directly to your own experience. You made the same experience. No, we need agriculture, but we need also power plants. We need the steel factory. We need the refineries. So therefore, water is, with the discussion about water has to be started very, very early, and the water distribution has to come to a conclusion. That's very important. And our environmental ministry said, well, no one has to stop showering now. It was something like a joke for me. Not very. So we have also developed a national water strategy, which is also including, and therefore you are not the first one in all around the world who applying or have created the idea to transport water from one place to another. It's also included here in the national water strategy of Germany. So as one solution, it's not the only solution, and only in the worst case we would apply this. But nevertheless, you can read it, or if you understand German, you could read it. But nevertheless, you can trust me; it's included in the strategy in general. Now coming, maybe it's good to translate a little bit now.
As I said to Jonas, I think we can have a discussion on some question.
Okay. So again, please raise up your hand or unmute your microphone if you would like to ask a question when I'm giving the presentation. So I'm very open, and I would like to hear some response from you. If there's any question, please also write in the chat. So my colleagues will look for the chat. I'm not able to do so right now. What is the situation globally? 20% of the water demand is related to industry. As you know, the largest demand is related to agriculture for sure, but 20%. And the question is it rising? And that's a very important question. From my point of view, to give you a short answer on this, no, because you can increase your production capacity without rising your water demand or your water usage. It's not a consumption. That's also very important. Industrial wastewater can contain also non-natural, difficult to degrade, and toxic substances. So I guess some of the colleagues from the universities and the others have heard about micropollutants, they have heard about microplastics, and for sure industry is releasing also micropollutants, the pharmaceutical industry, for example, pharmaceuticals, but and also microplastics. But the amount of the substances which are released are not related to the production, they are related to the population, to us, as we are using the plastic products, as we are using the pharmaceuticals. And therefore, that means all of us, including me, we are releasing those substances into the environment. And finally, via the municipal wastewater treatment plants. But it's contained, so we have non-natural, all the substances which are difficult to degrade, and which is also which has to be discussed with respect to the indirect discharge into wastewater treatment plants, into municipal wastewater treatment plants, because they are flowing through and finally ending up in the water bodies. Yeah, that's mentioned already. Significant emissions, often not from manufacturing, but from customers, from us, from the population. And it's another statement which is true for the future. When we are more in the transition into circular economy, the industrial circular economy. So we have the biologicalization. So more and more processes are going away from oil-based products or into renewable substrates which they are using for the production, the biologization of the production processes. So at the moment, there is a very, very strong shift, what I'm observing. There is not much information available in the public, but I can tell you from my work in the specialist group that a lot of development is taking place at the moment. However, even if you are moving into a biological production or using of renewables for the production processes, water is and remains and will be the most important solvent for industrial processes. That's for sure. And additionally for cooling, because it's the easiest way to cool, to evaporate water or by direct cooling. And that's something also which you know in Isfahan. So we have regionally very different state of development of water availability and pollution. If you're looking at the global scale, so you are in Iran, but if you're looking to Turkmenistan, for example, or to China, or to Indonesia, Australia, or to Chile, to Bolivia, we have completely different situations. And therefore, we have to look at the regional scale. That's the main message. And what we also observing all around the world, we have projects actually running also in South America, in Chile, lithium production, which will start soon. We have a project at the Pacific Islands, at Fiji, where we're looking for water supply. We have a project in Vietnam for industrial water reuse. We have projects in North Africa, starting from Morocco via Tunisia to Egypt and Jordan, and finally to Iran and Qatar. So we have many, many projects all around not basically more or less all around the world. And what we are observing, there is increased competition, not only in Iran but also in other places all around the world. And it will become even stronger, this competition. That's also for sure. If you look at the huge irrigation projects in Egypt, for example, where they're taking about 10% of Nile water in the southern part of Egypt, not in the Nile River Delta, but in the southern part of Egypt, it's clear. So this water is missing downflow in the Delta River, where a lot of agriculture is taking place. So the competition, even amongst agriculture application, will increase. Yeah, largest demand is due to cooling in many places. In Germany, we have a huge amount of water which is used for cooling, for industrial cooling and power plant cooling. It's the largest amount of water which is used all around Germany. But this is the case which I can show here briefly. It's not so important for you, but it's a German situation. We have 13 billion cubic meter for cooling, which is applied. And if you look at these numbers, they are much for production, for example, this non-public water use in 2019 is a very small amount. So the majority of water is used for cooling. Yeah? And you can say, okay, cooling is not so important because we are releasing the water afterwards. So, but if you are looking at evaporation cooling, you're evaporating water, huge amounts of water. No? So, and additionally, we are adding chemicals like antiscalants, biocides, in order to prevent biofilms in the heat exchanging systems, and therefore we're releasing also chemicals into the environment via this cooling. So it's not only the question of quality, it's also a question of quantity, both, and quality. Yeah, wastewater discharge in Germany in 2019, basically to surface water. The industry is discharging directly into surface water. We have in the public wastewater treatment plants, the on-site wastewater treatment plants. So basically it's released into surface water. So now I think something which I can skip or which I can briefly go through, it's a decline of the level of groundwater. These are data which we received from Inter 3. You can read it here. This is the publication where it was released in 2017 by Springer Verlag, Springer Publishing, and you can see that the groundwater. It's a pity that we cannot see the groundwater level, so it's a pity, but nevertheless, we can see that the wells have to be digged more and more deeper into the ground in order to get sufficient water supply. Yeah, this was the catchment area. That was also something, an outcome of our project, the IWRM project. Again, what we introduced to you earlier. So that's the water demand in order of priority. So first of all, households. The environment is something which we don't have to forget. No? So the green gardens need also water. No? And humans need these greens, in particular in the cities, in order to have, let's say, a balanced climate inside the city. So therefore, we do not have to forget. We should not forget the environment, which requires also water. Industry, important. I think that's nothing new, what I'm telling you. The contribution is 14% to the gross national domestic product in Iran, in the region of Isfahan. So it's very important, and largest amount again for the agriculture. Yeah, I will not go into all these details because I guess you know them, and finally you can look into my presentation later on. And reduction of water extraction by application of water management systems. It's something which is for sure. So you need water management in industry. You have to know where the water goes. What is the temperature? Not only the quantity of the water, you need also the quality. That means with respect to the composition, the carbon, the carbonous substances, but also the ions, the salts. You need the heavy metal concentration, and finally, you need also the temperature, which is very important. You know the specific heat capacity of water is extremely high, and therefore the energy which is related to temperature or to heat, to enthalpy in water is significant. Yeah, optimization, use of treated municipal wastewater is an option. With different qualities. So we can produce, we discussed already this one half an hour ago about the question whether to use an MBR, submerged MBR, or cross-flow MBR. Finally, you're producing after an MBR high quality water. It doesn't contain anymore any viruses, any bacteria, no? And it doesn't contain let's say, larger particles, but it still contains some organics and ammonia and phosphorus. But nevertheless, for some applications for cleaning, for car cleaning or truck cleaning or for anything, you can utilize this water directly. And therefore, it's also essential to think about different qualities which are demanded in industrial processes. Optimization of cooling, you see here's the power station. I guess you know this picture, or the power station. These are the cooling towers here in the back. And an option is to move a little bit away from the evaporation cooling into hybrid cooling. That means in the times where you have not sufficient water, that you support the cooling with electrical cooling. And last but not least, implementation of recycling technologies, which is already done or which is under implementation. Again, the question was already mentioned by my colleague. What's about the concentrates from membrane filtration? So going into the question, and that's most important. This would be one of my answers, or would be my answer to the question, which was asked before. So for me, it's very important not only to talk about recycling, but we have to talk about reduction of water use. That's very, very important. I know that the Iranian, and particularly the Isfahan located steel companies have a very low water footprint. I would say they are very competitive if you're looking at the worldwide scale. With the amount of water which is produced, which is used for production of 1 ton of steel. So there you have still, but I also remember an event when I visited Isfahan before the pandemic, when I went into one of the parks of Isfahan, and the gardeners just took a hose and let the water flowing out of the hose in order to flush. And finally, the water ended up at the street and flow away on the street. And this is something which should not happen. No? So that's very easy. That starts with the reduction. So in each and every place, we have to think about reduction and more efficient irrigation in agriculture, but also for irrigation of the greens should be more efficient, should be adjusted. And also at home. No? So the question, how much water do we need at home? So we personally ask yourself the question, how much water is really required? Do you need really 200 liters per day? Or do you need 80 liters or 50 liters as recommended, or which is a minimum of the World Health Organization? So I personally would say, to feel comfortable, I need not much water. No? So that's a question which starts with ourselves. So reduction is, from my point of view, besides the technological solutions, we should not concentrate only on the technological solutions. We should concentrate also on reduction. And modeling and simulation gives us a tool in order to do so. And again, working with the public, working with the people in industry, making them, increasing the awareness. That's very important. And reuse is something which is also very easy to do. So check the concentration. Reuse means you don't apply technological any technology in order to treat the water. Just reuse it directly. And for some applications, it might be possible. And recycling, we will discuss, or I will present you, and also already presented by Jonas, I will present you now in the following slides. So, but looking at the water drop, or what is in the water. And so therefore, it took, as I mentioned earlier, waste into brackets. So for me, basically, wastewater is first of all water. So that's the point. We have water. Unfortunately, in the water, we have also energy, already mentioned. So the temperature, calculate yourself. You can easily do so with the specific heat capacity of water. You can easily calculate the energy required to heat up water from 20 degrees to 40 degrees, or to 100 degrees in your boiler in the morning when you prepare your tea. You need a lot of energy to heat up. And for cooling, it's the same. So therefore, we have to take this into consideration, the temperature. So water, for sure, we have the inorganics, the salts and the metals, and finally we have the organics. Looking briefly at energy and what is contained in form of energy. So we have, I just have one example. You can change the numbers, but this is a beverage industry. So that means drinks are produced, which is a factory of 1 million hectoliter. Hectoliter is 100 liter. Sales beverage per year. That's production. It's a medium-sized production facility. And the usual wastewater production is 2.5. No, that's the mean value. You will find some of the factories which have less than 2. You have some around 3 is the mean value. So 2.5 liter, hectoliter, or cubic meter of wastewater per cubic meter, or hectoliter or liter of sales beverage, which is ending up with an amount of 250,000 cubic meters per year. No? So the DOC, the dissolved organic carbon, is in the range of 1.5 grams per liter or kilograms per cubic meter. You can multiply these numbers and you end up with 375 tons of DOC. dissolved organic carbon per year. So these are the basics. And what you can do now, you can apply anaerobic treatment. There are some assumptions which are quite realistic. 80% removal efficiency, biogas production approximately 0.75 kilowatt hours per kilogram DOC eliminated. You can double check these numbers. If they're wrong, you can come back to me, but the order of magnitude is okay. So finally, it's 225,000 cubic kilowatt hours per year, which you can produce, which is equivalent to 20,000 liters of fuel oil per year, which is covering 1.2% of the beverage industry in total. Yeah. Additionally, you can, if you're applying anaerobic processes, I think those people who are working with biological processes know this. Anaerobic processes do not need an aeration by definition. So you're saving a lot of aeration energy when you're removing the carbon anaerobically. And the side effect or the additional effect is that you're producing biogas, which can be utilized. So each and every time when anaerobic processes could be applied, you should do so. You should apply them. There are some limitations, some restrictions. So you need a certain amount, mass flow of DOC in order to apply anaerobic processes. And you need a certain concentration. You need a certain temperature, which should be above 30 degrees Celsius. I think that's not a challenge in Isfahan. And these are some requirements. But generally, first of all, check whether or not anaerobic processes could be applied. If so, apply them. That's as a recommendation. Yeah, it recovers energy from wastewater. So you're turning the carbon which is in the wastewater into methane and carbon dioxide. So 60% methane and 40% carbon dioxide. But generally, what we can observe, there's only a minor energy benefit out of this. No? But you can get a very simple and cheap treatment of the wastewater by anaerobic treatment. There are some other processes under development. You can also anaerobically produce H2. There are groups working on this. You can also use biofuel cells, but this is under development. So if you look at the heat energy, the same situation, the same plant, the same factory, in German conditions. In your case, the well water might be a little bit, the temperature might be a little bit higher than here, 12 degrees Celsius. Wastewater has 30 degrees, and just taking into consideration the temperature difference between wastewater and the supplied well water. So we're ending up with 5.2 million kilowatt hours heat energy. It's just heat. It's not electrical energy. Be careful. It's heat energy, which is equivalent to 0.5 million liter of fuel oil, which is 30%, roughly 30% of the beverage industry consumption. Again, be careful. It's heat energy. You know? So if you need heat, okay. If you don't need heat, you can forget these calculations because it's not electrical energy. It's just heat energy. Yeah, just as an example that it's important to take the temperature into consideration, the enthalpy of wastewater or water in all these calculations and before making a decision. So organics, already mentioned by Jonas. I will just skip this, some pictures from Tunisia again. So this was already introduced by Jonas. This is the olive mill effluent, which is nowadays still discharged into open ponds. Looks like this here. Dark brown ponds where the water evaporates slowly because we have the oil, thin oil film on top of the water level here, but nevertheless evaporation takes place, but also the infiltration into the groundwater. No? It's smelling and it's not a good situation. And these are some information about this, what already has been given by Jonas. It's the award which we received, Sami Zayadi and me. So looking at water, and now we are moving into the industrial water supply and asking the question, where is the water coming from? No? So it could be surface water, it could be groundwater, it could be tap water, it could be alternative water resource like processed wastewater. When we talk about wastewater recycling, we can also harvest rainwater, which is done also in some industries in Germany, like Audi in Ingolstadt is doing so, or The airport in Frankfurt is also harvesting the rainwater, but frankly speaking, it's only a small portion of the water supply which can be covered by rainwater. And municipal wastewater, the recycling of municipal wastewater. We have already a project in Germany, 900,000 big meters per day in the northern part of Germany, where a municipal wastewater treatment plant is extended to reverse osmosis, and the reverse osmosis the water, the permeate, is fed into the industry. No, so it's a project which is existing in Germany. We have other examples in Europe, in the Netherlands, for example, where municipal wastewater is still used for industrial applications. From my point of view, it's not too bad, because when you're thinking about population always gets water. That's the first priority. No? If there's water shortage, more population always gets water. That's for sure. And as a population gets water, wastewater is generated. And then municipal wastewater is generated. And you can, if you're using the municipal wastewater, we have a very safe supply of water. So therefore, for me, it's an option. It's a good option to think about. A second argument for municipal wastewater is that the salt concentration is, let's say, in compared to seawater, much lower. In the Gulf, we're talking about 4%, more than 4% salt concentration, sodium chloride. Now, in municipal wastewater, you're talking about maybe less than 1%. Yeah, depending a little bit where you are, and but this is the experience we made in Tunisia. So therefore, we have much less reverse osmotic pressure, and therefore the energy costs are much lower. So the treatment, when you have water, it must be treated for industrial applications, so can be treated for by bank filtration. If you're talking about surface water, flocculation, precipitation, ion exchange, filtration, disinfection, distillation, membrane separation, oxidation, and reduction. For example, in Berlin, in Brandenburg, in the area surrounding us, we have to remove iron manganese. Now that's a challenge here in the groundwater. And sulfate and nitrate. So finally, we are producing process water. And this is also very important to look at what kind of process water is required. No, it's surface water, not just for some flushing, for some cleaning, or we have boiler feed water. We have requirements with respect to conductivity, because otherwise your boilers will be blocked, where we have a lot of serious scaling. So therefore, the conductivity should be less than 10 microsiemens per centimeter or so. We have cooling water applications. We have ultra pure water. We have demineralized water. We have drinking water. We have water for injection for pharmaceutical industry, and we have just softener water. So you can see here different water qualities are required in industry, and that's also a question which has to be addressed. What water quality is required? No, therefore, you can provide water from recycling which can cover these requirements. And this mentioned here, different water qualities and raw water treatment increase economic efficiency of water recycling. Yeah, that's an example for water and energy management for PVC production in Spain. It was a European funded project. I will not go into detail, just showing you that, that modeling and simulation gives you a very good overview on the water usage and possibilities to increase the efficiency of water in production facilities. At the left-hand side, we have the raw water supply. In this case, it was well water. And what you can see here is the cooling water cycle. It's the largest amount of water which is pumped around in a cycle. We have here down, we have the water treatment consisting out of biological treatment and reverse osmosis. And all this is coupled. And this, therefore, simulation is very important. And my colleague Norman Schweimans will go into details later on with respect to KI, application of KI and simulation and control of those processes. So you can imagine that if something changes here in the production facility or something changes here, you would like to change something in the wastewater treatment, wastewater recycling unit, it's influencing the production process. No? So for example, if you're applying magnesium or alumina for precipitation here in this treatment, you have dissolved alumina. And this dissolved alumina can cause might cause a problem here in the production. Might. No? So therefore, it's essential to check the whole water scheme, the whole water flow and to manage the whole water and additionally the energy flow inside production facilities. Yeah, and water recycling, this is an example also from beverage industry. As time is running short, not time is running short, I'm too slow, I have too many information. So we have the beverage industry. Usually pre-treatment takes place, then we have alkalization, acidification, which is very important. Anaerobic treatment, flotation, aerobic treatment, again a flotation, microfiltration, and reverse osmosis. But these processes you all know, they're energy consuming and they're producing concentrates. No? So we have the problem of salts, the fouling and the scaling on top of the membranes, but usually we are producing this as the concentrates. And keep in mind, usually the recycling of water is limited, no? Limited to basically the tendency of scaling of the water. So the hardness builders in the water are very essential, and this is something which you can calculate easily in front of the design of those processes. So we have the salts. This is a production process. Here's the industrial process where we're adding salts and heavy metals. We have the water treatment. And again, we are part also of the problem as water engineers because we are applying also salts. No? So we are using salts for precipitation, for flocculation processes, etc. And they are all finally ending up in the membrane processes. And the membrane process generally is very simple because it's just physically separating one flow from another. So we have one flow entering the membrane process, as you can see here, and two flows leaving the membrane process. One is the permeate, high quality, no problem, we can apply directly. And the second flow is the concentrate. And this is something which we have to address, and which we are addressing since roughly 10 years. The concentrate management, the concentrate treatment. Now, out of this, you can increase the water yield, so you can reuse more water, recycle more water back into the production, but you have to care for the brine processing. And the best way, as already mentioned, is the reuse of the salts. But be careful, who is requiring, who needs such an amount of salts? Makes the balance again. So how much salts are you producing out of these water recycling processes? That's the first step. We did it last time. I do not know which application. So you can easily produce 3 trucks per day of salts when you completely crystallize the salts. So depending on the size of the plant and the industry you're looking at. Yeah, and this is an example which I brought with me is the salt recovery from the coffee production. A facility, they're producing instant coffee, this granular coffee, which you might know or which you know. This is a wastewater which looks like coffee. Yeah, it's brownish, and this is an effluent even from MBR membrane. In this case, a submerged MBR. Then the reverse osmosis ending up with a high quality permeate. You can see it here, but also the chemical analysis showed that underlines that the concentrations have or that the water has a high quality. But now we are moving with into the concentrate question. No? So the concentrate, all the colors are in the concentrate. So we have something like an espresso now. That's a usual common coffee, diluted coffee, and here's espresso. So higher concentration of hardly biodegradable substances because all of the substances which are degradable have been removed in the MBR. So those which are contained here are hardly biodegradable. So if you evaporate and crystallize, you end up with something which looks like coffee. No, this is a mixture of salts and organics, but there's no application. You just can depose it somewhere. No, get rid of it. But no, in this case, it was about 0.5 ton to 1 ton per day of this kind of material, which would be produced if they would apply this process. We developed a process, a so-called HighRec process with different technologies in order to produce high-quality salts, sodium carbonates, sodium chloride, and potassium nitrate. And additionally, we have organic waste and we have water for reuse. So it's an example. So we need a clever management and treatment and management of the brines, which are resulting not only from coffee production, from all industrial processes where you're applying water recycling. And this is also valid for other recycling processes or processes in general where you're applying membrane-based process. Could be cooling water, could be drinking water. Wherever you're applying membranes, you're producing these brines. And you have to think about what to do with the brines. You have to generate solutions. And what we are doing is now, that's the team, by the way, HighCon project team, with many industry partners, industrial partners, but also partners from research, from Fraunhofer Institute and authorities. So what we are doing, if we have such a project, we are making an estimation, the IM balance, metal concentration, composition of COD. We are performing the laboratory tests, and we have a process we can develop out of this, a preliminary process scheme and a rough cost estimation. The optimization of all inputs are into water. So that means we need to integrate water and heat model. So out of this, we're saying we are just moving one step back in order to see what can be prevented. No, that means the 3 R's. The first one, reduction. The reduction of salt intake, the reduction of heavy metals, the reduction of organics which are added to the water, and also reduction of water consumption or water use. And then finally, the process, optimum process scheme, depending on the local conditions. Not depending, for sure, it's depending on the energy price, transportation space, etc. We received the Resource Recovery Cluster Best Practice Award in 2019 from the IWA, and for this approach. And now we are moving to the last chapter, which I will keep very short, interaction industry municipal wastewater treatment plant, which is illustrated here. So we have a situation today. We have the households, we have the municipal wastewater treatment plant, and we have the industry here in this block, and we have agriculture here. So the largest amount of water, as you know, is used by agriculture, which partly is returned back into the groundwater or to the surface water, depending a little bit. We have the industry, which sometimes has a wastewater treatment plant and is discharging into the municipal wastewater treatment plant with or without pre-treatment, or could discharge directly into the surface water. This is a situation today. And what we can think about, or what we are developing to, is a symbiotic approach. So that means that we are catching all the rainwater, that we're using alternative water resources. That means the water from the wastewater treatment plant back into the production in order to generate alternative water resources, but also to agriculture. Because this wastewater here contains a lot of nitrogen and phosphorus, the nutrients which are required for agriculture. You can, that's an approach. But additionally, you also have to focus on internal recycling processes. We call it production integrated recycling of water. So go into production facilities and look where you can recycle water or reuse the water directly. And but also as the end of the pipe solution, you can treat it in such a way that you can use it. And additionally, if you have other processes, if you have, for example, industrial park, the effluent of one of one industry could be the influent for the other one. So the so-called symbiotic reuse or recycling of water. Yeah, what are the perspectives consistently applying the 3 R's, which I mentioned? Reduce, reuse, and recycle through water management industry using digitalization. Predictive might be an option. Regulate discharge of readily biodegradable materials. So this makes sense that the wastewater treatment plants, the biological wastewater treatment plants, are doing this job. In-plant recycling and use of highly concentrated steams in aerobic sludge treatment is a good option. Option of using clear flow of municipal wastewater treatment plants for industry. You have high quality water infrastructure. You have the people who are managing these processes with respect to the concentrates, the cost and sustainability. You have everything there that might be an option to produce the water over there with high quality or different qualities. The only challenge which remains is the logistics, because as soon as you're recycling water, you don't have to forget, need a lot of pipelines, you need a lot of storage, you need a lot of pumps, no? And you have a high, or you have a certain risk with respect to biological contamination, the growth of microbes, no? Legionella, for example. And these are some concerns which you have to take into consideration while designing such a recycling system. Yeah, and watershed management or integrated water resource management to secure water supply together with all users directly addressed by this process, the integrated water management, water resource management in the Zayandeh Rud basin. Yeah, thank you very much. That was my presentation. We have an international team. I am in the group, so from different countries, and yeah, looking forward to your questions.
Thank you. From a timing perspective, we are 6 minutes behind, but if there are questions, 1 or 2, we can answer them now. Okay, maybe we just go on and have a question discussion session after the last presentation.
May I have a short question? As you said during your presentation, we may face the accumulation of salts, organics, when you recycle in a closed loop the wastewater. The appearance is very good and very effective. You obey the sustainability laws, but when you treat the wastewater and then recycle it to the process, if you do not remove all the elements, maybe some of the, for example, salts or as you said, some biological agents maybe accumulate the process and may harm the process. Should we only monitor and control is the only solution for preventing such accumulation? Is it the only solution for?
Well, you can predict it. No? So it's from my point of view, it's easy to predict what happens finally. No? So we have a lot of programs, freeware, for example, for the reverse osmosis process or the membrane-based processes like WAVE and others, where you can have a good idea about what is happening, what is rejected, what's not rejected. And you, as researcher, can apply also some, let's say, basic tests about the rejection of the membranes. What is essential, so finally, in the concentrate is clear. No? So we have to care for the concentrates. We have to apply maybe also activated carbon adsorption. We have to apply advanced oxidation processes. There are many questions open and they are case dependent. No? So because when you're increasing the salt concentration, for example, you have a lot of, for oxidation process, you have a lot of OH radical scavengers. No? So the question is, where is the best place to apply, for example, oxidation and ozonation? It is good to apply it in unconcentrated wastewater or after a certain concentration. You will find arguments for both. So that's one point. That's the concentrate side. Yeah, and the other point, with the other argument or the other issue is, which I didn't mention, is the permeate. So reverse osmosis is not rejecting 100%. No, that's for sure. It's just a solution diffusion membrane, and therefore some substances are passing through. We know it since many, many decades from Orange County in the United States. We know it from Singapore. So you have a certain amount of substance which are passing through. And this might cause, and I think this is your question or your remark, this is something which we have to think about and to see whether or not there's an accumulation which has negative influences on the production processes or on the environment, whatever.
Yes.
And this is something we have many experience. We applied reverse osmosis for many industrial processes, or for some, let's say there's as many as maybe 10 or so in total, or 15. And each and every, on most applications, we figured out there's still a slight let's say, color in the permeate, slight yellow sometimes. We have also the odor, some smell. Now, with pharmaceutical industry, we have investigated this, and also a small amount of carbon and other substances. Ammonia, for example, is also a matter of concern, and therefore you can observe worldwide. In United States, for example, in California, they added, after reverse osmosis, they added an oxidation process, an H2O2 UV process, after reverse osmosis in the permeate, not the concentrate. And that's very interesting.
Okay. So
yes, there's a question in the chat. What is the rate of rejection? That's depending the rate of rejection. No? So as I mentioned, so for example, the number I have in my mind for the treatment of municipal wastewater after MBR by a reverse osmosis, we are observing, or what I have in my mind in the publication, the DOC is in the range of 1 milligram, 1 ppm, 1 milligram per liter, maybe a little bit less. Yeah, in this range, let's say it's like this. I don't have it exactly in my mind. You can check the literature. But there are colleagues from Singapore, they investigated this and they looked what kind of substances are those. Yeah? So this is a matter of concern and we have to take this in consideration. So the message is, the go-home message is, reverse osmosis is not rejecting 100%. It's rejecting much above 90%, but not 100%. And this is something for research. No? So you have to look in the future. We, as researchers, we have to, what are those substances? Are they hazardous? Are they accumulating? No? Etc. So thank you for the questions and the comments.
Very well. Okay, I think looking at the time, it's good to continue. There we go, Norman Schweimans, my colleague from Berlin, is with us. And thanks to Hamid, we have a short introduction or short summary of the publication of the presentation in the chat. For now, thank you, and the floor is yours.
Hello, good afternoon. My name is Norman Schweimans. I'm member of the team of Professor Geißen, and my background is industrial engineering. So now I will talk a lot about models and digitalization, or digitization, how it's properly the better description. But for now, I can't take the presenter, so I can't give you a presentation.
Sorry, Masoud? I think, Masoud, you need to give the presentation rights.
Okay, I find his name and I
Norman.
Mm-hmm. Starts with N, yes?
Yes.
For me, towards the bottom.
It works now.
Norman Schweimans. Yes, that's right.
But German
yes,
should
exactly.
work now.
Oh, okay. He has the.
Yes, I think so.
Yes,
I gave him the right.
Yes, you did it.
Yes. I will now share the presentation. Can you now see the presentation in full screen?
Perfect.
Yes.
Okay, great. Yes, hello again. Thank you all for your interest in this presentation. I will now talk briefly about how we tried to use digital tools to improve the operation of a large industrial wastewater treatment plant. As Professor Geißen just said, it's important to improve treatment performance, to be able to reuse and also save water in the end, and maybe even stop contaminants from entering the water bodies again, because a high salt concentration can have a bad influence on the water bodies. So our goals for the digitalization for wastewater treatment were to, on the one hand, see how the plant behaves when we change the load scenario. So if the influent changes, if there are additional productions, so the load increases. And on the same, or at the same time, it was a goal for this project to give recommendations for the operators of the wastewater treatment plant, because it is always good to have a fallback or something else that monitors the operation of the plant besides the operators that are there in the control room. Because we all know accidents happen, people are not concentrated all day long, and so it's always good to have a fallback. And to do this, we try to build a bridge between two worlds. The old world was the activated sludge model. That's a process model that relies on ordinary differential equations. And on the other hand, we tried to use statistical and neural networks to forecast the plant performance to some point, because with the differential equations, you don't have the option to look into the future. You can always only calculate one step further, and that doesn't help in real production. So what we did, and what is the most important, by far the most important thing, if you want to do anything that is related to digitization, or how it is called in Germany most of the time, digitalization, the collection of all available data. Because everything that should give an outlook into the future, or everything that is to deliver sound results for models, needs massive amounts of data and good quality of data. And that's why in the second step, we analyzed the dependencies between the different data structures, so that we can also replace, for example, missing data in one time series with data that is calculated from another time series. That's overly important. Then the real models were created in the activated sludge model family to show the real layout of the plant we are looking at. And after that, we added kind of checks and balances that monitor the performance of the simulation all the time. And that's how we managed somehow to have a digital twin. That said, digital twins for biological processes are almost impossible. So we started this project with a goal that couldn't be really achieved, or no one believed that it could be achieved. But we started straightforward, built, you can see here, that's the classical layout of a plant realized in, we use a software called Zimba. It's a software that can calculate activated sludge models. We use this one because we are Germans and that's a German software. There are a lot of different softwares you can use. Some of them are freely available on the internet, like Modelica or Stoat. If you need them, you will find them. And but the challenge remains that if you look further, activated sludge models were designed for municipal wastewater, and we are looking at the industry. So everything that works well about these models relies on good empirical data that was collected over years and years by research teams all over the world. And for municipal wastewater, if it's real undiluted municipal wastewater with no industrial influences, then the composition is kind of stable. And in addition, parameters that can influence the process are also limited. It's rain events, storm events, drought events, but that's relatively easy to tackle in a model. When we look at industrial wastewater, we have a completely different story. So usually we have very limited data on the very process we are looking at, because in industry, mostly every wastewater treatment plant is different from the other ones that exist, because it's another industry, or it's another size of plant, or another production process, and so on and so forth, or simply another industry. So often you will find variable characteristics of influence. That means sometimes there's a high load of COD, sometimes there's no load, depending on the production circuits, or also other contaminants, chemicals, whatever. Then you have often, because of cleaning processes and stuff like that, variations in pH, and because again of the production, a very variable rate of biodegradable COD, so BOD5. So this changes again, and this all requires adjustments to your model if you use those activated sludge models. In addition, high temperatures and low phosphorus concentration and so on can make your life really hard. And in our use case, that's, if you wonder why do you even think about it, we have some huge production parks in Germany, and this one we were looking at is 7.5 square kilometers. It has 25 kilometers of sewers, and there the influence that is treated in the wastewater treatment plant comes from 100 different productions, and those 100 different productions, even each of them does batch production, changing batches, different cleaning programs. So this, influent characteristics are really quite changeable. So on the right I have for a slide overview how the rate of biodegradability changes over time for these influence, and that's how you need to change your model over time. And that's why we spent a lot of time thinking about how we can make those activated sludge models, these are the third step, a little bit smarter in a way. So first we looked at what is there as raw data from the existing plant information or process information management systems. And as already mentioned, then we looked how can we improve the data source, because those activated sludge models have a certain vector of inputs that you need to fill. Otherwise, the results are not good anyway. And then we looked how we can optimize all the different parameters of those models, and found a way to integrate, on the one hand, statistical models, and on the other hand, those classical activated sludge models, to have some kind of artificial intelligence solution to adjust a model in a way that it can somehow work like a digital twin. And this information that is produced by the final model can then be fed back to the process management system and even to the control room. But more on that later. So again, this is the model as discussed before. So this is what has a lot of parameters, like here the primary clarifier. You can change all kinds of rates for the separation. Then for the biological treatment step, you can change from the aeration to all kinds of hydraulics. In the model, you can adjust a lot. And here, that's basically the heart of the modeling for biological process. In there are a lot of equations that basically describe the growth and decay of the bacteria that remove the COD. So in total, let's say you can adjust more than 100 parameters that all change the performance of the model a lot. If you now think about doing a sensitivity analysis for all of them on your own, you will spend half of your life just doing that. So that's why we thought about an infrastructure where here, where it says Simba Sharp Session, where we had a system of virtual machines, virtual computers that run those models, and a controller that does all the sensitivity analysis for us. And in this model, you remember the flow sheet, that was the blue thing. Here's an example. We first took for the COD, the calculations that are kind of standard in literature for the calculations, and this is the orange line, while the blue line is the real measurement of the online measurement system at the plant. And then this is one of the models we applied. We used statistical models that draw on various time series to not directly calculate the COD from TOC, but to improve it. And you can see in many places here, it's not really the case, but in many places like here and here and here, we could decrease the deviation between measurement and model by only one step. But to have a good result, you have to do it a lot of times for different influential parameters. And that's why we use kind of interfaces between the software that does the ASM stuff, Simba, and our logic in Python. And there are, briefly different ways to do it. At the one hand, the Python library takes or draws the data from Simba to do all the calculations and comparisons. And on the other hand, it writes to the configuration of the model file to make the changes that are necessary to improve the model. This also allows us to do a global sensitivity analysis. That means analyze the sensitivity of all parameters that are in the model or a subset of those parameters, and also get an insight how the change of one parameter influences the change of another parameter. So that's what you can see here. That is basically those factors govern how the model calculates the different fractions, like easily biodegradable, hardly biodegradable, inert fractions of the COD. And we could see here from the analysis which factors have the biggest influence and which factors are influenced most. So we could create a short list or a priority list which parameters to optimize the model for. And in the next step, when one parameter is selected for optimizations, we use the interfaces to vary the value of this parameter and do different simulations with kind of a break rule. So if the results of the first step of the static simulations are already worse than the other ones we had before, then the second step, the dynamic simulation, which is a much more time-consuming step and CPU-consuming step, is just not done. And this way, we slowly made our way to optimizing the model further and further. And as a last step, because every change in one parameter changes a lot of things in the model. So most of the time you won't only improve the model, or you will improve it in one metric, in one goal you have. For example, getting closer, for example, for the COD measurements from the model to your measured results. But this oftentimes means that the results for nitrogen or your results for suspended solids in the sludge will get worse. So we, in the end, used multi-criterial parameter selection so that we can see which kind of adjustment has the best overall performance. This little red dot here, in this case, in this little example, is the one that was best. This describes a whole set of parameters in comparison to other parameter sets that we had identified before. And that's already really complex, but that's only kind of for understanding how a classical model can describe a complex industrial water treatment system. In the end, we had to rely on additional statistical or statistical or other not deep learning models, but models that can be trained to learn on new data, so that don't only look back, but also can learn on new data, and this way create a system that can predict the plant performance for a certain number of time periods. You can see that here. The green line gives a preview of the next 3 hours, and the blue line again is the real measurement. So it is not perfect, but in the end, here you can see it again. The green one is a prediction, the blue one is a measurement that followed on later. For a good number of parameters, you can have good results with statistical modeling when the input data is cleaned and stable and there are not too many errors in the measurement. And to summarize, when, like in this industry, the influent characteristics keep changing constantly, the creation of a digital twin is complex, to say the least, because the simulations are only stable for defined operational states. Like in municipal wastewater treatment, it's easy. Then dynamic simulation is not sufficient. You need to dynamically adjust your model, otherwise it will work maybe for a day or two, and then the results of the model will differ a lot from what you measure. And so that was the basic steps again that go beyond of what I've shown in the beginning. The model design and validation, that's basically what was in the first flow chart. And then what we then did is characterized model performance by metrics. Those are the ones that I have shown you in the multi-criterial optimization, so that you can look at different performance indicators at the same time and select your parameters and then use them automatically in conjunction with continuous comparison of model and reality to adjust the model accordingly. One of the big benefits of this system is, and maybe you have thought, why don't they just send it to some cloud, this cloud, that cloud, whatever cloud? We are working with industry and they don't want to share their data with anyone. So that's also a little part that we had to take into account. We had to work with existing structures, existing data management systems, and we implemented it that we have virtual machines that are located inside the network of the data owner, so everything stays on site. And we also only accessed relevant data of the information system and could give it back to the information system where process control systems, so the control room, would take our data themselves. So we had no active access to the process control system, which is very important for security. And yeah, that brings me to the summary. So the integration of plant operations and models are surely beneficial on multiple stages. The first and most important step is a hardened data. So for every step in production, basically it's very beneficial that you have better data. If you know your data, you can easily spot errors in machinery, in plants. It's always good to have hardened data, and it's the very first and most important thing you need for digitalization, and digital twins. And if you then have this data, you can create strong automatization of your modeling process. And later, if the model has been running for a few months and years next to the control system, and it basically gives a good and realistic result of your operation, you can also use this model for automatization. However, a lot of people think, okay, digitalization, we can now start something digital, and then we don't need anyone anymore to run the process and to be in the control room. That's sadly not true. You will need a lot of human control for a long time, because those models, even if they use artificial intelligence, need to learn, and they need to learn a while. If you compare it, for example, now everyone talks about ChatGPT and how powerful it is, but a lot of the magic you see in ChatGPT only relies on the fact that this thing learned whole Wikipedia. So if you ask this thing something, it just replicates. If you ask something that the thing really doesn't know, the answer will be poor. So that's the same for any model you can train. It only is as clever as the data that you feed to the model. And nevertheless, if you you integrate models and data repositories, it will increase the reliability of your models and the understandability, and at the same time you can create something like soft sensors that is basically control structures that will tell you if a sensor is faulty or something else is wrong, because what models can easily do is detect patterns and standard behavior. So if a sensor is completely out of range, a model will directly spot the difference. But yeah, that's what I can say now from our case study. And yeah, the summary or the takeaway is there's a lot of potential in digitalization, but there's also a lot of work and you have to spend a lot of time. Thank you for your time and your interest, and I hope it will be somehow beneficial to you. Thank you. Are there any questions?
Thank you. Hamid Amiri raised his hand.
Thank you, Norman, for your great presentation. I enjoyed very much about using digitalization for upgrading the wastewater treatment plants. I just wonder if you tell me more about which level of analysis or data have you been used in your, for example, you may consider microbial interaction and deep analysis of the wastewater for better results. Which level of analysis have tried before?
Exactly. So this is what you just said, the interaction between the different bacteria is the most important thing that is missing in this kind of model. Frankly, we were not able to use it because we don't have access to the data. So we had limited access to the sludge and to the labs on site. They have their standard procedures that will be measured, and everything that goes beyond is usually outsourced because they don't have the staff to do more analysis. And we got some results, but nothing that is enough that comes back to data to really build a model on that. That's in fact a big topic in research that for our estimation is a lot too unpopular right now, because the models we have now are not fit to represent what's really going on in industrial wastewater treatment. So if you have any insights on this topic and bacterial interactions, then we are always interested.
Thank you so much. And another question I have, would it be possible to integrate these kind of model in the online controlling of the whole process? Have you tried it, or just saying that you told us that there is some recommendation for the control man?
Yes. So basically, this the system really runs along. So there are two parts that you could see it in the beginning. There was one basic calibration with historical data that is not running all the time, but the models that kind of forecast the plant performance that run along with the plant control systems on site, and the forecast is fed back to the control system, so that the operators can see if the difference in the forecast and the actual plant measurements gets bigger. So if the model deviates a lot from the measurement, they get a warning, kind of, please check if the process is running like it's supposed to be or if something is wrong. That's everything that we could implement in the frame of the project. Again, if you train the model more, or if you add some input, like if, for example, the effluent values of a certain type, for example, the nitrification, denitrification process is out of range, then please check if the aeration systems all work as expected, or are there any toxic influence, because in this case, because it's industrial, they also have a lot of toxic stuff that needs to be removed first and is controlled online. And the challenge is, getting back to your question, to really take into account the whole process chain, because it's quite complex, and for some of the neutralization and removal of heavy metals and so on, there are no models that you can just take into your chain of models, but you have to create them, and this takes a lot of time.
Thank you so much.
Thank you for the questions.
There's another question for you in the chat, which is, could you please tell us more about the novelty point of this work?
So the novelty point of this work is that as I said, we are trying to build a bridge between the old world and the new world. The novelty approach is that we use tools that are usually used to train artificial intelligence models or neural networks, to kind of, on the one hand, adjust process models, and on the other hand, also use those artificial intelligence modules, mostly statistical, because in a lot of time series applications, they are still superior to neural networks, to improve the input data, and improve the input data in the way that the data that is fed into the classical process model is highly polished, so that there are less errors in the process model. And on the other hand, in the end, the results of the process model are augmented with results of parallel running artificial intelligence models, so that in the end we have a mixed model result. But I have to stress the fact that if you purely rely on artificial intelligence to forecast plant performance, you will usually have very poor results. Because again, training is very crucial for all kinds of artificial intelligence models, and there is often in process monitoring too little data to give them a really sound understanding of the process.
Wonderful. Two people raised their hands. Masoud Tayreyun, if I read this right.
Yes, you can read Farsi also, and it's interesting. Thank you for your presentation, Mr. Norman, and it was very interesting for me. Yesterday, I thought that it is about, for example, instrumentation and controlling, the digital controlling of wastewater, but as I see, it's the simulation approach in treatment plant. Two questions. One is as you said, digital twin. It's the way that, as I understood, that is a combination of for example, AI with, for example, process-based modeling, as we say the black box modeling and the process-based modeling, you mix them and you can present a novel method, and it's very interesting, I think. So
yeah,
it is first. So as I understood, it's a combination, and the second I want to say is the different softwares you mentioned. But the main was Simba, as I remember, and Simba. Do you have any? Can you mention some any difference? Because we tried to. One of my students wanted to work with Simba, and it was not open. It wasn't free, and we should work with another software. I want to tell me a brief advantage, disadvantage of this software in comparison with other software.
So yes, so on the first hand, at first, this software, this project I was talking about in the last 20 minutes, had a kind of a lot of special things you have to adhere to. One was that it's a massive treatment, massive production site with very limited data available. That's why we chose this approach of white box modeling, because there's simply not enough data for a pure black box model. So we had to combine two types of models. And even for the white box model, the data is quite limited. That is kind of the novel approach of the project itself. Do some kind of digitalization, automatization of process control with a very, very limited set of data. So they only have, let's say, 20 or 30 time series that are measured online. The rest is artificial intelligence that creates more time series from correlations and additional data that was collected from historical, sometimes even handwritten information. So that's why maybe this approach seems clumsy for a lot of applications, but for this application, it was the only thing we could do. But for the software, you ask about the software. Simba is, yes, it's not free, it's paid software, and the advantage of the software is that you have a lot of examples included with it. So people spend a lot of time to create example flow sheets of different treatment plants, of different treatment technologies. And if you have this software, you can just, if you need to build a model of your plant or a flow sheet, you can just go to the examples and have a look at them and copy and paste what you need. That's a big advantage of Simba. The logic behind it, so the calculations it does, those are freely available. Those activated starch model family, for example, for biological treatment, it is published in papers for a long time. So there are different solutions you can find that are freely available. One of them is Stout, but the software is kind of really old and also hard to get used to. And then there is another one that is called Modelica. You maybe have heard about it. Modelica, that's a kind of a scripting language for models that are not limited to water and wastewater treatment. You can build models for everything, including electrical, machinery, even aviation engineering, all kinds of models you can do with it. And this software is also freely available, and then it's called Open Modelica. And for this software, there is a library that is called activated sludge, something that is exactly what we have calculated here. So you can also use this free software if you like to test it.
The link for Open Modelica was posted. Thank you.
Thank you very much.
So there was one hand in the Jafari, please.
Thank you so much. I have a question from Herr Professor Dr. Geißen. As you said, hydrogen production from wastewater is under development. I would like to know, from your point of view, what are main challenges for industrialization this process, hydrogen production from wastewaters? Thank you.
Yeah, that's let's say a statement which was made by me a couple of years ago, maybe 5 years or 6 years ago, and related to the anaerobic processes. So nowadays it's another, let's say, this statement is another environment. So, but starting first with the anaerobic processes, you can turn as you know, the anaerobic processes are producing H2. By themselves, and you can move this transition, or you can increase this transition in producing more H2. As best as I know, the groups working on this topic, turning the transfer into more hydrogen are not practically applied in full scale. That's my knowledge, but I didn't check it for, let's say, 2 years or 3 years. So maybe there are new information available. The second point is the production of H2 from water, because the electrolysis process, and therefore the application, for sure, the H2 production requires water, and let's say comparably large amounts of water, but nevertheless the quality must be very high, and that's a challenge. And therefore the question arises, if you have no water, okay, that's a possibility to produce it out of wastewater. But where you have water with a higher quality, you should apply this. You should use this kind of water. So water quality is of high concern for electrolysis. And this is nowadays, I think we are on the way into the hydrogen production in Germany, worldwide. But taking raw wastewater and producing out of it water for electrolysis, it's challenging. It costs a lot of money. And this is something which has to be evaluated very carefully.
Thank you so much.
And the same, by the way, with biofuel cells. No? So it's also a question, because you have these material challenges. And again, as soon as you have, let's say, nutrients in the water like nitrogen and phosphorus and potassium, you will rapidly have a growth of bacteria. And this is to control this in water is really challenging. Additionally.
Thank you.
You're welcome.
So there's one more question in the chat. Given the process data, is it possible to develop a model without ASM?
Yeah, I just started to write it back into the chat, but yes, in fact, it is possible to have results without ASM at all. But the challenge is, if the process then changes too much, the model, for example, if another stage of pre-treatment is added, you need to add it to the model as well. For the white box model, like the ASM model, you can do that by adding another process stage. For the model that only relies on data, you first need to collect a lot of data of the new layout, and then you can run a model without ASM again. This is how the things work. So the models, the black box models only work, so artificial intelligence models only work if you have a good history of data. And for the plant, how it is now, you can get satisfactory results without any ASM interaction. But as soon as something changes about the plant, then the historical data doesn't describe the current state, and then the artificial intelligence models are not good anymore. That's what I can add to this point.
Yes, Masood.
Excuse me, it took time, but because I was asking two questions, I forgot my first question middle of my explanation. My first question was, is your method can be generalized in other processes, for example, membrane simulation or other field of engineering, your method?
So the optimization step can be generalized, yes. As long as you have a model or some kind of calculation, you can do that. So the optimizer itself can be adapted to other kinds of calculations, yes.
No, for simulation itself. Can be a way of simulation for limited data. Simulate every process other than because you focused on biological process. Can be generalized.
Yes, we focused on that because this was the real treatment system. So this plant we were looking at, they have about 40,000 cubic meter a day treatment of industrial wastewater with biological treatment. So that's what they do. That's why we modeled exactly that. But you can also model chemical physical treatment or membrane treatment. If you somehow can describe your treatment process, you can do this model as well, yes.
Thank you very much. Thank you, everyone.
Wonderful. We are just in time, I guess. If there aren't any additional questions or topics that we should discuss, I would like to thank everyone for coming to our webinar. It's nice to see that it's always nice to have a discussion and to see so many different representatives from the Iranian side. And I'm sure we will have 2 more events at least to discuss what, broadly speaking, innovative technologies. So these will be 2 more talks about technologies which are currently still in development with a technology readiness level below 6 or 7. Technologies which are a potential technological solution to, for example, reject water or other challenging water streams. This will happen in the months to come, and we will spread the information via Dr. Masood and Dr. Hamid. And so from my side, I just want to thank everyone. And
yeah, thank you very much also from my side. Thank you also for organizing, Jonas and Azad, and contributing Norman to this presentation, and all the team of the Chair of Environmental Process Engineering in the background, but also to our hosts from Isfahan, to the 2 colleagues. Thank you very much. And if you have any, let's say, questions, any concerns with respect to the topics we presented, but even further topics which are of interest for you, please contact us. So fortunately, we have the project which is funded by our Ministry of Education and Research. That's a great advantage we have in order to keep the cooperation living in these turbulent times. And I'm looking forward to cooperate with you with all of you in the future. And from my side, warm goodbye.
Thank you so much. I want to thank you for your great presentation, Sven, Jonas, and Norman. I also want to thank all of the audience and who are from university and industry and also in Persian. ممنونم از همه شمایی که تو این جلسه تا الان تشریف داشتید. امیدوارم که جلسه خوبی بوده باشه و همونطور که گفتن چند جلسه‌ای در آینده دارند در ادامه بحث‌های مرتبط با IWRM و خوشحال میشم که ارتباطتون رو حفظ بکنید. Jonas, we also have a platform for sending emails, I guess. Yes? We can ask everybody if they want to share their emails and being in contact. You're
yes, more than happy then to have you send us your email addresses, and then we will make sure you are notified of any upcoming events or opportunities.
Maybe you can... Thank you very much. And okay.
It is clear where to send the emails?
So you can...
The address?
Either you can send the email addresses to Hamid Amiri or Masoud Tahir-Yoon, or to me, to myself. I guess we showed the email addresses during the presentation.
Yeah.
If you write your email,
you can post it in the chat again.
Yeah, if you
can send it in the chat, write their email address in the chat, and
I can copy them. And,
maybe Azad, you can copy paste them, and then we have a list to start with.
Okay, thank you for your time. It was very interesting and informative for me, and I think the audience has been enjoyed such newly presented information on wastewater, and hope for the following sessions. And thank you for Jonas coming to Isfahan, and great visit we had to the treatment plant, and a very challenging discussion we had when visiting and in the sessions. I hope more collaboration can be developed in future. Thank you.
I hope so as well. So goodbye for now, and hope to see you for the next session.
Goodbye. Nice to meet you.